Hey guys, welcome back to more thermodynamics. We have been talking about enthalpy and we learned a new value yesterday which we were calling entropy. Now, enthalpy is looking at the heat of the system, and that's one way for us to figure out if things are favorable or not. And now we know entropy is looking at how messy the system is. So if things are getting messier, that's making the universe sort of smile here. It's a favorable situation. So there's two things that we can use to figure out if a reaction is probably going to happen or not. However, sometimes we find that these don't work for us all the time. So let's look over at notability real quick here. The example I have is ice. And we see in this picture and in the equation that the ice is a solid and it is turning into a liquid. So if we're sort of analyzing this, we could take a look at it and try and decide what's going on with my delta H and what's going on with my delta S. So with the delta H, is this endo or exothermic? We think back to our little heating curve here. And this is a solid, this is a liquid, and this is a gas. We know that in order to go from a solid to a liquid to a gas, energy is going into our ice cube. And that's causing it to turn into a liquid. Into. This is an endothermic reaction, and our sign for endothermic reactions is a plus. This is not a favorable reaction, right? We can see this boulder is rolling up the hill. It's gaining energy. So this is not a favorable reaction. And according to delta H, this reaction should not work. But if we look at the S, you have a solid, which is a crystal and extremely organized, turning into a liquid, which is messy. And that's something that the universe typically smiles on. And so we would say, yes, the degree of disorder, the entropy, the messiness is increasing. So we have one that's not favorable and one that is favorable. So who do we trust? What's going on here? Well, most of us should be aware that sometimes ice melts and sometimes it doesn't. What decides whether ice will melt or freeze? And the answer to that is temperature. So when we have these values at odds, when they're arguing, we want to look at the temperature. In this example, if the temperature is really, really, really low, then all of a sudden the delta H is more important, right? If you put this in the freezer, it is not going to melt, and we can trust what delta H says about the reaction. Delta H says it's not going to melt. But if the temperature is really, really high, then we can trust S. S says that it will melt. So we need one more variable that's going to help us use temperature to decide which of these values we can trust. And that value is called Gibbs, Gibbs free energy. And we have ways of solving for Gibbs. We have a couple of different ways. But the key here now is what we want when we're looking at reactions. We want our delta H to be negative. We want our delta S to be positive. And these will tell us if it's favorable or not. But in the end, delta G, we want this to be negative. This will tell us yes or no. Will the reaction work? It's not saying, hey, this will probably work, right? These are probably. It says, yes, it will work, or no, it will not. It's going to take these two values that we have up above and decide who we are allowed to trust. And so this is delta G. Now, when we go to solve for delta G, there's a couple of different ways. You'll notice that when we look at our paper here, we had delta H and S. Well, there's also a column for delta G. So we can solve for delta G the same exact way that we did for H and S, products minus reactants. But there's another way, and it saves us a little bit of work. So this is the way right here that we've been using, products minus reactants. But like I said, temperature is important. It helps us decide which one we can trust. So in this particular example, we've got an equation that's using temperature. And so we can see that temperature is going to give more importance to one value or the other. So if the temperature is really, 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 really small, then we can trust whatever delta H is saying. If the temperature is really, really, really big, it's going to make this value super important, and delta G will trust the S. And so we can just use this equation to quickly use values that we've already found. So to give you an example of how this works, the equation that we solved yesterday for delta S is right here. So I thought I'd save us a little bit of time and recording space here and just recopy it down. So this one we actually did in yesterday's notes. We found that negative 242. We saw that the messy was disappearing. It was getting more organized. And then I went ahead and saved us a bit of time and solved for delta H. We've done this products minus reactants thing enough times that we've got it there. So if we wanted to, we can do the same thing. We could do one more of these for delta G. And I looked up the values. They're shown right here. So we could do products minus reactants again. But why? We have this equation, delta G equals delta H minus T delta S. And we have the values right here. So why do this whole long process again when we can just subtract? So we're going to put our delta H in. So that's negative 891. Minus the temperature. Now the temperature, when we look things up out of the back of the book, you'll notice that we always have this little symbol right there. That means standard conditions, and that is 298 Kelvin. So unless they give you some other temperature to work with, we assume 298. And then we had one other issue we have to watch out for, and that was our units. When we're looking at our units, this was in kilojoules per mole, but when we looked over here at S, it's in joules per mole Kelvin. So we need the units to be the same. So if this is joules per mole Kelvin, we just need to move our decimal 3 places. So we get negative 0.242. And so in the end, when we finish with this problem, we end up with negative 963 kilojoules per mole. Kilojoules per mole is the units for our delta G. So that's why I moved it into kilojoules right here instead of leaving it joules. So we look, and my sign is negative. So for delta G, if it's negative, that's a good thing. It means that the reaction is spontaneous. It will occur. We're not saying it might occur. We're not saying it's a favorable reaction. We are saying this will happen. It is possible at this particular temperature. Now, if we change the temperature, it might not happen, right? If I was to raise this temperature up really, really, really high, it's going to make that delta S more and more important, and it's going to basically start making delta G trust in S a little bit more. So this is the idea. This is what we're looking at. Your assignment, we're just going to basically do the same worksheet you did yesterday. Yesterday, you found all your delta S's. So what that means is today, you will need to find your delta H. Sorry for my writing here. Your delta H and your delta G. And I want to know everything about this reaction. Is it exothermic or endothermic? Is it spontaneous or not? What is happening to the messiness? So you can work off of yesterday's numbers. I would probably just find your delta H like that and then use this equation to solve for your delta G. That's probably the fastest way. If, however, you want to do it products minus reactants, that's always also an option. Just know that if you find your delta G using these values up here, it will be slightly different than if you find it using this equation. They'll be close, but there are some differences there. These values are averages. They're not locked in all the time. There's a little bit of variability there. So don't get upset if your answer's slightly different and you solved it a different way. So let me know if you guys have questions, and we'll be in touch.